invite our next speaker, Mr. Nils Klassen, Technology and Sales Manager, M10 Solar Equipment, GmbH, Bills Tech International Limited. So please join us and everyone gives a huge round of applause. The topic is going to be Shingle-Matrix technology for GW manufacturing.
Okay, good morning everybody, and thank you for joining us today. I'm here on behalf of my company M10, as already mentioned, and our partner from India, Bills Tech. And I'm going to present to you, let's say, an innovative technology, how a future module could look like. And we're talking about the Shingle-Matrix technology, and I gave it the second title, how you can stand out in today's PV market. Because, well, if you look at PV module products today, I just brought some examples. And what we can see is, well, three things. They're 95% from China. Every of those modules is looking more or less the same. So we have these half-cut, wire interconnected module layouts. They have this very distinct center line. They have a very good efficiency today. They have a very good appearance, and they have a very high quality. So what can we do if we want to step into that market, into that very interesting and growing market? And how can we stand out beside these products which are presented today? And our answer to that is, well, make the module look different, make the module operate different, make something different that from the beginning tells your customer, I'm having another product for you which is not coming from China, which is something different, and this is the Shingle-Matrix technology. And, well, you can see it's more or less a black plate, right? But it hides the fact that there's, okay, no pointer, but it hides the fact that we have shingled solar cells, and they're arranged in a different way. I'm going to explain to you a little bit more about this, but just from the appearance, you can already see it's a major difference to any existing product right now. And to further understand what the technology is, we take a look into the cross-section of a module, right? On the left-hand side, you can see what's happening in a standard module, ribbon or wire interconnected. And on the right-hand side, you can see the corresponding shingle module. And what we know already is, well, in the standard module, we are interconnecting our cells with wires from the front to the back side of the neighboring solar cell. And in case of the shingle module, it's a little bit different because we're slightly overlapping the solar cells, and we are directly bonding them together, like it's the case for roof tiles, for example. And this is where also the name shingling comes from, right? And in order to bond the solar cells, we are using conductive adhesives. So the entire technology gets rid of soldering. There is no solder anymore. There is no flux anymore. We're just using industry standard electrically conductive adhesives and use them to bond the solar cells. This is a sketch you see on the right-hand side below. This is how it looks in reality. So you can see two solar cells, the one on top and the one below. This is a cross-section, so we can also see the module glass, we can see the encapsulant, we can see a 3 layers back sheet. And what we can see is in between the solar cell, this orangey-looking part of this image, this is the ECA. This is a copper particle-filled adhesive, and this electrically and mechanically bonds the solar cells together. So this is how this looks in reality. The size of that is, let's say, roughly 30 microns times 500 microns. So we're talking about a very, very small amount of ECA, because everyone always asks, well, these things are costly, right? ECAs are costly compared to solder, but you use below 1 gram for a standard-sized module. So cost is not an issue anymore because you need only very few amount of these expensive materials. Coming to the advantages that technology brings you, we again take a look at cross-sections, and we again take a closer look to the region where two solar cells are neighboring each other. So on the top side, you will always see the wire interconnection, on the bottom side, the corresponding shingle sketch. And the first thing I want to talk about is that wires cause ohmic losses, right? They're low, but still, it's a component. It's not free of resistivity, it causes some losses. And since we got rid of the wires by directly bonding the solar cells, you also get rid of these ohmic losses. That's one important thing to keep in mind. The second, and this is the most important advantage, is the geometrical advantage, because you need space on your PV module area to bring the wires from the front side to the rear side, right? So there's going to be a cell gap. It's small, but this is still more or less that area in your PV module. On the other hand, if you overlap the solar cells, there is no that space in your module anymore, or let's say it's drastically reduced, right? So that's a very important advantage because we can increase the packing density of our solar cells to the limit, right? And a third thing is optical advantages. Well, wires cause shading, right? So it's a component on top of your solar cell. You have been seeing this before. You can see the structures of the wires. This causes shading of your solar cell and where a wire is and the corresponding metallization. There's no light penetrating to your solar cell. So that means you have also some dead areas on your solar cell itself. In principle, this is happening for a shingle interconnection also. But now here's the smart thing. Since these shaded areas, I sketched them below also in yellow, are on the lower side of your solar cell, we just covered that up with the active area of the next solar cell. So we don't care that there's shading structures on our solar cells because they're hidden beneath active layer of the next solar cells anyway, right? So that for, let's say, usually referred to CTM losses, so cell to module losses. But there's a fourth very important aspect, and this is an enhanced shading resilience. And I'm going to spend another couple of minutes explaining what I mean with that. But this is, for me personally, one of the most important aspects of this technology because this really pushes your energy yield, right? I know we're used to selling kilowatt peak, but in the end, it's important how many kilowatt hours you produce, right? And this is, yeah, a very important aspect, and this is a property Shingle-Matrix technology brings with it that strongly increases that. Okay, take a closer look on the topology of that module. You already saw in the beginning, it's kind of a masonry-like structure, matrix-like structure, we call it that for that reason. And that means we're taking those shingle cells, you can see them, the large ones, and you can see a half-cut shingle solar cell, which is highlighted in red. And if we're using these half-cut solar cells, we can create this brick wall-like, masonry-like structure, and that brings the electrical properties with it to increase the shading resilience. Because ultimately, that leads to the fact that every solar cell within one row of our module is being interconnected electrically in parallel. That means their currents add up, and they stay at the same voltage level. And then if we go through our module, every row adds a small fraction of voltage, and in the end, we end up roughly at the same IV characteristics as a standard module does. But as said, this first thing happening within each row, this parallel interconnection between solar cells, this is what's really pushing the shading resilience to the limit, okay? Because we are building these bridges by using this, you can see the small fractions of metallization shining out in the cell gaps within one row. And this is a current path, and this is an operating current path. We have been able to show that. So there's actually, in case of shading events, there are currents flowing via these small metallization structure all the way from the left of the module to the right of the module. That means, for certain shading scenarios, there's currents bypassing the shade. And I guess every one of you knows what happens if you take a standard module and have such a diagonal shade over your module, covering in each segment of your module one solar cell. The thing is that there's no currents coming out of it anymore because you shade every solar cell. It's a series interconnection. No currents are flowing anymore, right? This is not the case with that technology. So there's a lot of scenarios, a lot of cases where this is happening, right? And the second thing, as mentioned before, is the parallel interconnection because we are having a distributed current generation, right? We're not generating, it's a very kind of a little bit abstract to think about, but we're not producing currents on a square-like structure or on a, let's say, rectangular half-cell-like structure where all the current is produced on one spot, so it's very easy to cover that. No, we're having a distributed current generation which distributes on the entire length of the module. And this is a great difference. Okay, enough of that, but how can we prove that? That's the more interesting thing. And we did two things. We did a lot of simulations, a lot of computations of such scenarios, and we did also a large experiment. And to start off with the simulations we did is, we investigated the 4 common structures of a PV module present today, right? We have the past standard, everyone knows that, full square solar cells. We have the present standard, which is we call it butterfly layout. You have this upper block of half cells, you have this lower block of half cells. Then we have the shingle string layout, known from SunPower, Maxeon, which have been launching their products in 2015, 2016. And then the next step from it, the Shingle-Matrix approach. It's kind of similar to the shingle string approach, but in a way it behaves very different. I again highlighted the half cells with orange just for you to recognize them. And how can we now compare these 4 layouts? Well, we can use a Monte Carlo approach. We can just throw like numbers at the problem and just compute, And then in the end, we will get the average power output. And this average power output at a certain point won't change anymore. And then we can be very sure that we see differences because, well, this is the law of large numbers, right? If you compute enough scenarios, you will get a very reliable average power output or an average number. And in that case, it's going to be the power output. And this is what we did. So we built an electrical model from that. We created random scenarios, random shading scenarios, computed the IV curves, the IV characteristics, and analyzed them in order to showcase the differences. So, and it's a problem to compute many of these scenarios because I'm not going to detail why this number below is so large, but if you just think of I'm going to throw random spots on my module and I'm going to assign them a certain illumination, just random, you'll end up with a number of scenarios you cannot compute anymore, way out of the range of computing anymore. But here, Monte Carlo strikes because we have been able to show we don't have to compute 10 to the power of 180, crazy large number. We can show that with a couple of thousand computations, you can already reach a converging average power output. And even more, we're interested in having a look at more realistic shading scenarios because what you saw before, this sigma zero sum is, well, shadings are not looking like this. Shade does not look like this. Shade looks like the one on top, so we have such rectangular shades. And we sometimes also have these, let's say, spherical clustered shades from leaves, from whatever, bird droppings. And we can just randomize those scenarios and compute. And what we get in the end is this result. In both cases on the graphs, you can see the average power output over the number of scenarios we computed, right? And you can see if you take a look at the x-axis that after, let's say, 1,000 to 2,000 or 4,000 scenarios, we already have a value which is not changing anymore. And on top, I again showcased the 4 layouts we investigated. The 2 green ones are the shingle approaches, and you can see there's major differences, right? If you take a look at the y-axis, the average power output, we can see that in case of the Shingle-Matrix module, the average power output for rectangular shades, so if you have rectangular shading, your average power output will be something like 35% of your initial power. In case of the old standard, it's going to be around 11%. So that's a huge difference. It's factor 3, right? There's a huge difference when shading strikes. And, well, this is simulations, and I guess most of us know, well, with simulations you can do a lot of stuff, and it's always important to keep in mind what the boundary conditions are. But we also did an experiment. We took those layouts, we created an artificial shading situation. You can see that we took such a PVC tube, we aligned it over the modules like this, so we can achieve something like a sundial. So the shade is moving across our module throughout the day and creates a dynamic shading situation. And then we just left that 7.5 months outside from August to March. And every 5 minutes we took an IV curve, and from that we get a very good idea of what the yield of the system is after those 7.5 months. And again, what we see is major differences. On the y-axis, you see the cumulative specific yield. That means how many kilowatt hour per kilowatt peak installed PV module did we generate over this period of time. And again, we see those green lines are the shingle approaches, and this blue line is our reference module with full square cells. And we can see that in case of the Shingle-Matrix module, we ended up at roughly 500 kilowatt hours per kilowatt peak installed energy, installed power. And for our reference module, it was around 160. So again, we have major differences between those 3 layouts. So we have those simulations, and we have those experiments which showcase, which in my opinion really prove, that if you have shading, there is a technology which sticks out, which is really making a difference for your kilowatt hours produced energy. And now we're getting to the second part of my title, Sales Manager. We have a solution for that. So our company, over the last 4 years, developed a machine which is capable of producing such modules, which is capable of interconnecting such modules with a very high throughput. So we can achieve, with one of those machines, up to 150, up to 170 megawatt peak per year production capacity. Strongly depends on your cell efficiency you initially put into the machine. So we have a real solution for that. And besides that machine, we also have the next step, the auto busing and cross-connection solution. Not want to go too much into detail of that machine because we're here on the exhibition. We're on booth R951. So if that interests you, you're invited to join us in Hall R and visit our booth and talk to us, and we can explain in more detail and also explain more to you what our equipment is capable of doing and how it can help you and how it can support you making a difference in the very monotonous PV module product market right now, right? And with that, I'd like to thank you. Together with me is one of our CEOs, Mr. Marco Saladin, and we have our team from Blistech, our partners here in India, Sanjay Kha and Rakesh Raina, which are here with us. And the four of us invite you again to join us in our booth and discuss with us. So thank you for your kind attention, and if there's still time for some questions, I'm trying to answer them.